from universities. Today I will give these topics about towards high-speed continuous variable key distribution in real-world conditions. This is the outlines and I will take 3 introductions. Firstly, I will introduce the CVQVDs and about the revelations and the experiments. And secondly, I will introduce the research on high performance CVQVDs, especially about the high-speed CVQVDs in our groups. And thirdly, I will introduce the real test of CVQVD networks, which is our recent work. Finally, I'll give further directions about the CVQVDs and give some summarizing. Okay. Firstly, let us take a reviews on the progress of realization of the Gaussian the CVQVDs. And this is the first Gaussian modulated CVQVD experiment in this work. And the source it used coherent state is proposed by Gaussian group in 2003. It is used the component trainers is the free space and use the BSS to simulate the losses. And the CVQVD can reach 1.7 megabits per second for loss-free channels and 75 megabits per second for 3 dB loss. And they use reverse reconciliations. You should remember that this CVQVD are estimated under the individual effects, and this experiment lays the foundation for Gaussian modulations. CVQVD as a key schemes in the following studies, and now its security has been good. The third one, in 2010, our groups have developed integrated CVQVD systems. This system has 2 parts. The first part is the CVQVDs. The second part is the KCQ encryptions. Based on the CVQVDs, we can implement the CVQVD point-to-point across 27 single mode optic fiber, and the average key rate is 4 kilobits per second under the collective attacks. The system's frequency is 500 kHz. By using this KCQ screen encryptions and combine the CVQVD systems, we use the CVQVD systems. The keys generated by the CVQVD systems, we realize some data encryptions, and practically we realize the real-time voice transmissions. We call it the quantum telephone, the quantum cryptographic telephones. The third one is the circular secure test systems. It's one part of the COX project and in France in 2012. Also, it has 2 parts. 2 main parts is first part is the CVQVD systems, and another part is classical symmetric encryptions. They test these systems for a long time, about 6 months, and the systems by using this CVQVD system, it can realize about 18 kilometers optic fibers in about 5.6 dB across these 2 cities. The average key rate reached 600 bps under the collective attacks, and the system frequency is also 500 kilohertz, and they use the 128-bit AES encryptions. So we can see why the CVQVD has not been used. There may mean some limitations. First one is we can see it with the distance. Now, the conventional CVQVD schemes, we know that the security distance is also is about 100 kilometers, and the widely used asymmetric cryptography is not limited. And the trusting node, we can use the trusting node to longer and increase the security distance, but it is not a good solution. And we can use the quantum repeaters. So the quantum repeaters are required. Now the second one is speed. The speed, you know, the physical parameter estimations over large blocks we always many times, and hardware drift, latency, and so on. We also restrict the speed of the security systems, and finally, the secret key rate. There are not enough secret key rate for one-time hack, so I think it cannot be used. The last one is the security. But the security we call it, we mean it is practical securities. Since there is incomplete security proofs for practical applications, I think, because there are some imperfections for any devices of the practical systems, and there exists distance between the proofs and the practical implementations. So we consider the limitations. However, the CVQVD has some merits. The first one is that signals are compatible with the WDMs, which greatly is itself deployment into the communication networks. Secondly, the CVQVD was expected to achieve higher secret rate rather than the DVQVD protocols, since to the possibilities of encoding more than one bit per pass. We can conclude summarize the characteristic of the conventional CVQVDs. We use amplitude and phase field as a measure to encode the secret key rate as a secret key, and we use short line limited coherent detections, and the component is a standard, and we use the WDM to integrate the signals transmitted from the classical signals and the quantum signals, and the securities, theoretical securities have been fully approved, and finally the range is about common about 25 to 80 kilometers, and the key rate is about 10 to 10 kilobits per second. We can see this memories. Before I introduce some improvements about the performance of the CVQVD, I will take a brief introduction about the Gaussian modulated CVQVDs. This is the protocols. It goes to the following steps. First, the Alice, I will take a brief introductions. Alice shows the data XP from the two-dimensional Gaussian distribution to result a coherent state displayed in X and P and send it to Bob. Actually, Alice will use amplitude and modulus and phase modulus to implement this protocols. And Bob measures second step. Bob measures either quantum X and quantum P. It is decided by random values from the phase modulus in Bob's local lines. We use this, and Bob declares whether he measured X and Y and X and Y, and Alice discuss the uncorrect conditions. So after this, Alice and Bob perform parameter estimation, the reconciliation, and the secret implication to distill the final case. So what is the secret key rate, and how to estimate it? So first we will introduce why the CVQVD can distill a stream of secret key. They must certify that there are the two conditions. The first one is that the home-done detector must reach the short limit to detect a signal, that is short noise. The variance short noise should be larger than the electric noise, and the mutual information between Alice for much larger than the one may link to if that is the R is firstly. R is also, so we can conclude that R is a function of much of these parameters, include the data block size, and the modulation variance, the excess noise from channel, short noise, variance and transmission efficiency, the efficiency of the Hamilton detections, the electronic noise, and the efficiency of reconciliation, frame error rate. And the security rate can alter the collective text in the we can variate in the estimate as subtopic and finite size scenarios. We calculate these equations. IAB, the mutual information between Alice, Bob, and she. B is the linked formations. And in finite size areas, and now we'll extra linked information from the privacy and verifications. So we can also conclude some phenomena about these R's, about the description about these parameters. R will increase with the frequency, some data size, and R decrease with the excess noise, and BA has the optimal values, and the secure distance increase also with the data block size and the efficiency of the detections and the verification purpose also decrease with the excess noises. So we conclude that the performance limitations. First, for range, we can see the range limitations include 5 factors. First one, the excess noise, is from the imperfect relation relative to the phase estimation linkage of example from LO for limited isolation. And secondly, the loss of LO passes the lower powers of the LO will decrease with and errors which may link to the and the errors will less than the electric noise. The third one is the sensitive of Hamilton detections, even at low SNRs, and the error correction efficiency even at low SNRs will also limited into final side effect. Also, we can find that the high bit rate limitations also includes many of these factors about the secret, the excess noise and frequency modulations and data acquisition speed, Hamilton detections, and the speed of error corrections and efficiency of error corrections in the frame error rate. We can conclude that all the excess noise and the efficiency of error correction both limits the performance of the ranges and the high bit rate of the CVQD schemes. So, in 2013, Pulse group, they did a good job, and they proposed high efficiency reconciliation protocols, and they actually realized that the CVQD is over 80 kilometers of optic fibers. The efficiencies and the efficiency of reconciliation reached 95%, and they can also consider the finite side effect. So now I will introduce our works on this to improve the CVQD. As shown here, because the excess noise also restrains both the ranges and the high bit rate of CVQD. So our track is to control the excess noise in CVQDs. Firstly, we developed high sensitive Hamilton detections. These detections have some we designed this Hamilton detection with these considerations. First, we use the quantum efficiency, high quantum efficiency pin deltas, and we use TEC coolings, and we lower the electric noise, and we can reach the short noise linkage detections when the oscillators of optical power is 6 orders of magnitude larger than the functions of stimulus. We can see from these figures, this is about 6, 10 to the 6. This is it is 2 orders magnitude lower than the conventional Hamilton detections. So we can conclude the advantage of this Hamilton detection. That's the cooler on-die detectors require to lower its power of LO to reach the short noise limit, which removes the restrictions on the distance and the lower power, and the lower power of LO quite decreases the excess noise emitted from LO. The second method to controlling the excess noise is that we use high precision phase correlations. This is the mathematical representations of this error correlation, phase correlation schemes. When Alice sent X and Bob received Y, the delta C is the phase shift, and the phase shift value can estimate it by calculating the mathematical expectation of X multiplied Y. Values by these equations. And this is the performance. We simulated these phase correlations. When SNI is 10 dB and delta C is 170 and 35 degrees, and we get the derivations is only 0.5 degrees. When SNI decrease, we also forget that the derivations of the phase is also don't increase very small. This is the original message we increase very large. So this phase correlation schemes has this advantage that it lowers the actual excess noise from the phase drifting quantum channels. And so based on these key techniques, it is the high sensitive on-die detectors with the weak LO, the high precise precision phase correlations with low SNRs and high digital error correlation scheme. We realize the CVQAD beyond 100 kilometers. This is the layout of the of these systems. We use Gaussian modulated CVQAD schemes, and this is the practical the figures. We also consider the final side effect and this the secret rate is very small when it reached the largest security distance is larger than 150 kilometers, and when it reached 150 kilometers, the secret rate is very small. Okay, now I'll introduce some work about our work about the high-speed CVQADs, and we first proposed the sub-Korea's maxing CVQAD schemes in 2014, and we use the sub-Koreas. The sub-Koreas is generated independently by using voltage control oscillators and with different equations, the frequencies omega phase and E2, and they are amplitude modulated with the relays distribution and random numbers, and also the phase is they are phase modulated with the unit distributions 5 case. They are combined together by a bias voltage and lessened by core voltage. These schemes it can realize and allows that the distributions of n quantum channels of Gaussian modulated CVQADs. However, using these schemes, each channels will have a non-Gaussian extra source noise, and resulting in slight shortening of maximum transmission distance. We are slightly the systems will be shortened, and the transmission distance, while the total cyclical rate can be considerably increased. You can see from this figure the multi-channel gains will be close to the multiplexing numbers for the short distance. To achieve this high-speed CVQAD, we first proposed the high-speed homeland detections in 2003, and this is homeland detection detectors, and its bandwidth is 100 megahertz, and the maximum bandwidth reached 300 megahertz, and the noise to reactor noise ratios is 14 dB, and CMRR reaches 54 dB. And this is the bandwidth test. We can see that the noise power increased with the L powers, and the maximum values of MR is, we can see that the detector is well balanced and the first stage less than minus 17 dBm. This is the distribution of the average numbers of oscillator to the variance of output voltage. We can see the linear range is 1 to 6 multiplies 10 to the 8. And this is the conventional detection. Also, if we should realize the high-speed CVQAD, a high-speed reconciliation is necessary. We can see that the CVQAD contains two parts, main parts. The first one is the quantum communication part, and the second one is the data processing part. This is the data processing part. So to improve the high speed of reconciliation, to improve the speed of the the reconciliation, we should. There was maybe two methods. And the first one is we can decrease the complexity of decoding. The second one, we can improve the calculation ability. Because we simplify the calculations in the reconciliations. We use the vectorization and vectorization skills. Vectorizations can save a lot of operations and some memories, and the parallelizations, and also we can see that parallelization is not enough. Practically, some of the operations, just like the functional core, the loops, and the judgment, is also costly. So, and also we can see that the parity check matrix H is also constant for reconciliation. So we can use the parallelizations strategy to simplify the calculation and improve the speed of the reconciliation. We test this reconciliation schemes in the practical schemes with multi-edge LDBC code, where the code rate is 0.202, and the tolerance is 10,000. By adjusting the number of parallelized frames, we can obtain this result. We use the CPUs and GPUs to record, to compute this, to run these reconciliations algorithms. The blue curve is obtained in CPU, and the red curve is obtained with this GeForce. This GeForce devices, GPU devices. We can see that the decoding speed reached 25 megabits per second for GPU. So, based on this schemes, high-speed homeland detection and reconciliation schemes, we realize a high-speed prototype, CVQAD prototype. The frequency reached 25 megahertz, and this is the layout of this systems. It includes the optic modular and the control modular, and post-selecting, and the data processing modules. We test these systems for 12 hours, and we record the success noises. And we can estimated the security rate that it reached. The average security rate is 52 kilobits per second across 50 kilometers of fibers. So, to further improve the speed of CVQVDs, we developed 15 megahertz frequency CVQVD experiment. This is the optical layout of this schemes. It concludes the clock signals and classical communication signals and quantum signals. They have different wavelengths. You should mention that to suppress the Raman scarlings, the 1550 nanometers band is assigned to the quantum subsystem, and the launch power for the transmission for classical transmitters and transceivers at 1590 nanometer and 1610 nanometers band are tuned at velocity about -32 dBm. To achieve this high-speed CVQVD, we developed produce new high-speed CVQVD home lines. The integrated three amplifiers in small encoded package reduce the input capacities and consequently provide a much improved bandwidth as well as electronic noises. The bandwidth is 1 gigahertz and the electronic is from the 1 to 6 dBs. This is our test for the excess noises. We record for 1 hour. So the modulation variance optimized and the quantum efficiency is 0.5 and the battery noise is 0.3 in short noise unit and the practical reconciliation efficiency is 33%. You can see this security rate that we can reach 1 meg DPS and 25 kilometers. We consider the block size for 1 to 8. I should mention that the excess noise due to the noise contours from the local oscillator and the partial data channels in CWDM can be controlled effectively in about 10 to the -5 for partial channels and even very smaller ones. For synchronization signals. Also, to further improve the CVQVD's speed, recently realized the CVQVD without sentinel. That the experiment setup is shown below. That the frequency reach 100 megahertz. In other side, there's only quantum signals and in both side they regenerate the LO signals and they take homeland detections. I should mention that since Alice doesn't send LO signals, so they should have find a reference as a base reference. And here we randomly insert some of the stabilization paths to with these quantum signals to realize phase compensations. This is the two of the lasers in the Edison block. Alice side he used the TYQI2016 lasers as this wavelength and lengthwise is 1.5 kilohertz on both sides. That we use a tunable TYQI2016 lasers and lengthwise is also very 1.9 kilohertz, and we can use you can adjust the bias currents to place these two frequencies together very close and realize homeland detections. You should mention that the wavelength short-term stability for Alice lasers is 4 megahertz per hour, and the accuracy or deepness of frequency to be restricted to 20 megahertz, which is limited the wavelength resolution. On our side, we use also to take this experiment. And the local LO is operated at pulse mode so that we can achieve a high coherence between the short noise and electric noise and avoid the saturation of balanced homeland detection. You can see these results. There are two cycles pointed based on the block size, which is a subset of block size, and correspond to roughly 200 millisecond of the data precision. And the secret rate under radio attack in this finite size for 25 kilometers. You can see this. So this method we can locally generated LO remove the security loop from transmission of LO. Locally LO makes this high speed and short noise limited homeland detections more flexible. So this is the most important scenario. Modifying this receivers improved power of LO. Finally, I'll introduce our field test of CVQD network. This is the location of CVQD network in the house. There are 4 nodes. There are our 4 campuses of Shanghai Jiaotong universities. The level we can, the first nodes are deployed on standard communication infrastructures connected with the conventional telecom optic fibers. There are the topologies of these 4 matched metropolitan areas of CVQD networks. There are 4 nodes and 6 links. We can see from this network that it's very large for these losses, and maybe the network was built some decades before, so that was very large. And so this is a CVQD product, and it also includes more different wavelengths, and we use mux and demux to integrate these signals, classic signals. Also, for as a fierce table, there are some connectors and technical splices in this fierce fibers, and we'll introduce extra noise in this field environment, and we can bound these reflections. Noise can be also can be calculated. So, however, this extra noise is in order of 10 to the -7 and 10 to the -2 in short noise unit. This work finally we can reach this result. You can see for the large losses, losses are very large, and the excess noise is also large. We can generate security keys for these 2 links. And finally, we introduce further directions for CVQD. First is integration of CVQD system. We can use classical optical communication techniques, and the second one is stability or robustness of CVQD. We can use self-reference CVQD schemes. And the third one is packet securities. It is the MPI CVQD provide efficient ways to solve these packet security problems. And finally, the coexistence of CVQD with classical optical communication is very important, especially with the intense classical signals. That's all. Thank you very much.
So we have time for one quick question.
In one of your slides, you showed that maybe you attenuate the classical channels by 30 dB to avoid Raman scattering. Those slides about multiplexing. When you put the classical channels on 1.6 micron, then maybe, I don't know if I misunderstood, you attenuate the classical channels by some dB, like 30 dB?
Yeah, it's very low, and it can we attenuate these classical signals so as to decrease the excess noise from the skeletons, Raman skeletons. So, however, we should realize the classical communications. This is the first important things, and then we will consider the communication for CPQA, and we will try to control the excess noise from the Raman skeletons.
Yeah, but doesn't that contradict the claim that CPQKD is compatible with classical channels without touching classical channels at all? This was my question.
Maybe we can have this discussion later. Okay, so thank you again.